let me tell you about Michael real briefly here. He's one of the national leaders in constructed wetlands, primarily looking at their use for wastewater treatment, but also for stormwater. He's a civil engineer by training. His undergraduate degree was at Berkeley. He also has a graduate degree from the University of Chicago in systems. And he's the author of a book, which Constructed Wetlands and Sustainable Landscape, that is quite well known in the field and is a great reference literature in this area. He is the president of Natural Systems International. Their website is natsys.com. You ought to take a look and check out some of their projects. They've done over 450 of these projects across this country and in Canada and Mexico. And Michael was a member of our All-State Shanghai team this past summer, where we're starting to look at some of these technologies in China as well. So without further ado, I'm going to turn it over to him. And he's done the impossible. He's condensed it all into about a 35 to 40-minute presentation. By no means is this going to be exhaustive, because he could talk for days about the topic. And so if you're interested, please come back and visit us tomorrow morning at 8:30. We'll be in room 101 next door. So thank you, Michael.
Thanks for the challenge. The title, I guess we need some lights on here, please, so we can see the first slide. What I'd like to talk about is ecological design, and I'm going to talk about it from my perspective. I mean, this is a huge subject. I'm not going to claim that I know very much about it at all. In fact, I'd like to take everybody briefly through this so that you have a sense about the direction, the scale of the problem, the kind of issues that we're going to be dealing with. And I really truly look to the next generation. The students here, I hope you're motivated to do something. I plan to give you help. My generation is learning about this right now, and we rely on contractors in the nursery to be able to execute this kind of work. It's not just a design issue, it's an understanding of the actual natural system once it's in place. Implementation is a serious part of what we're doing. And I can't stress too highly that this aspect of this is extremely important. The main points that I would like to leave you with is that water is clearly essential for life. Development cannot take place without it. So any new project, this is especially true in my part of the world, the western part of the United States, we just can't put in new homes for people to live in if we don't have the water, and that's a real issue. Human activities are clearly responsible for polluting our water resources. What I like to stress and what I firmly believe in is that it is now possible for us to be able to do ecological design where we can actually ameliorate and improve upon the activities that have taken place before. This is a hopeful message. I hope that you agree with me when I'm done at the end of this lecture. One of the things that is a nice framework for me to work from is that 2,500 years ago, we had the basic four element concepts of how everything fit together in the world. It was nice. It was a nice handle. It was a fairly sophisticated concept, and I don't want anybody to diminish it in the sense that it's simplistic. I think right now, if we want to just rephrase it in the sense that land, air, energy instead of fire and water are still unnecessary elements for life. So whenever we look at a human system in relationship to the natural world, we're going to be dealing with the land, we're going to be dealing with the atmosphere, scientifically. Certainly energy is an essential part of this, and clearly water is also essential. What I think we're struggling with now is perspective, because we're going from a reductionist approach to these four elements, if you will, which in the case of, let's call it the land of earth, we broke down into 92 separate elements. Well, if we put all four of them back together in a holistic picture, what we're learning to do is to recognize that guys like me are educated as civil engineers and in fact work with the department. And the disciplines that go with the biology of the wetlands, for example. Very, very diverse kinds of people that I personally work with, is that we have to understand that the corrective problem is a team approach. we look or try to define the relationships, and this is really the challenge that I see. The simplistic images here are renewable resources for the energy source. Hopefully, we're going to get there with those kinds of things in the very near future. I think we have to. When we look at these kinds of relationships, I think it's part of the training, especially for landscape architects. And this is why it's always a pleasure for me to come back here. And I think that part of the education you're receiving is to understand in some way how those four elements have to work together successfully for our green community. When I undertake my work, what I look at is putting the word multiple ecology. This is such an essential element. I can't stress this too much. And the kinds of things that we typically do, the engineers have given these names. It's not like we don't understand them. We just don't understand them from an ecological perspective. The wholeness of a pond, for example, is very, very diverse ecology. It has aerobic elements on the surface, and anaerobic at the bottom, and anoxic in between, and the kinds of plant communities, microbial communities, the invertebrate population. It's very, very sophisticated. In fact, the treatise on limnology, one of the classic books done by some of the University of Wisconsin, 3 volumes of books stacking this literature. How can any one person hope to understand that unless it's their life work? So what I hope to do in my role in working with these kinds of ecologies is to bring in as part of the team that person who does truly understand, for example, the algal population that exists in the pond. The marsh is my specialty. It's one that I've come to recognize I know nothing about after doing this for all these years, and hopefully I'll know more about it, or at least more than I do right now. I find that I thought they were very easy for us to work with in the beginning. Well, now understood that these are extremely complex systems. We know they can work. We're so far along the line now in terms of our experience with them that we can put together teams of engineers, contractors, and nurserymen, and actually be able to build weapons that treat and clean up water. We can't predict exactly how they're going to work, but we can certainly meet permits that state regulatory agencies give. The meadow.
There it is.
Can everybody hear me now?
No.
How about now?
Okay, how about this one?
Yeah. All right, great. All right, so the final ecology that the meadow or the prairie is an extremely, again, pretty complex system, but we can now specify 572 different plant seeds to put in a prairie mix. In fact, it's in the federal specification. That's pretty remarkable, and that's a big progression from where we were, let's say, 20 years ago. To be able to specify it and actually implement it are two different issues, and I think what we can say pretty reasonably that in most places we can now implement the ecology of the tall grass prairie. That's pretty phenomenal for me to see that happen. From my perspective as an engineer, I use that prairie as a form of treatment. The nutrients that come from wastewater are actually very beneficial, and a great place to put them is into a prairie. The benefits for those kinds of ecologies is that they also are carbon sequestering systems. Ponds, marshes, meadows, forests take carbon that either comes from the wastewater or atmospheric carbon and basically bury it. And this becomes more important when you think about global warming, if that's important to you at all. As a concept, as an application, we can now begin to talk about ways in which we can increase the rate of carbon sequestration by combining wastewater with the carbon that's required for plant growth that comes from the atmosphere. This is a really important concept. In fact, work done at Duke University, published in Nature this year, shows us that by increasing the nitrogen content, which is an element in wastewater, on the land application in the forest, we can increase carbon uptake 3 times. This is new, and this is the exciting part of the technologies that we're getting into, is to begin to understand how we can interact in our efforts as designers to improve the conditions of the world around us. It's just beginning, and we're only doing it on small scales, but nevertheless, it's happening. Another fascinating thing that comes out for us is to recognize this concept of industrial ecology, where we have in wastewater, again, this would be from a municipality like Muncie or a big city like Indianapolis. We have nutrients in the water. In the wastewater, we settle out the biological solids. And in this particular example, those solids are used in the vermiculture program, earthworms basically, from which enzymes are extracted, which are a very, very high-value product and can be used in things like soil remediation, for example, or making detergents or purifying food products. The biomass that we come because we have nutrients in water again in a natural system, like a wetlands, we're growing lots and lots of plant material. That material, when harvested, becomes the substrate for mushroom cultures. Again, this is beginning ways of thinking, but just notice how everything gets used now. There isn't the concept of waste. So thinking about this stuff as we're turning what would normally be quote-unquote wastewater and the sludge associated with it, we're going to turn it into something else that is of more value. Okay, I can only talk about water in 30 minutes, so we're going to focus very quickly on the 3 elements of it. There's obviously the water supply, that's where we start. Every community needs water, and it needs to supply clean water. Anybody that's looked at the health statistics in the United States recognizes that one of the very important elements of the longevity of our population is the ability to supply our communities with a clean water supply. That is, in fact, believe it or not, it's a rare commodity. Even in the United States, it's becoming more rare. Most of the world, 2/3 of the world, doesn't have that opportunity. They're not drinking clean water. Wastewater treatment is a necessary consequence of putting drinking water into the house. So we're going to develop some kind of wastewater industry. Is a very important part of that. In the United States, only 4% of our total water supply goes into domestic use. The other 96% of that is used for agriculture and industry. Stormwater is another important element. When you build something on a site, pave it, put houses on it, you create conditions of stormwater runoff that have an impact on the surrounding watershed. And as we are now recognizing, there's a significant amount of pollutants that go with this. In fact, the new federal regulations that are implemented in 2002, in April of this coming year, require that every municipality have a stormwater management program in place that actually treats the water that runs off from our streets and buildings. The scale of the problem, the real message is here, if you go into this kind of work, you're never going to be out of work because it is a huge problem. Some population statistics. This is always mind-boggling. You go to make a trip like Shanghai, or as I do occasionally fly over Los Angeles or go near the city, you recognize that the planet is developing these mega cities. There are 23 of them in 15 years that will have more than 10 million people. Shanghai currently has 17 million right now. New York City is at 16 million. Half the world's population is going to be living in cities. Just, if you have anything to do with city development and you realize what kind of pollution problems are created by these kinds of cities, you think, how do we solve these? This is, to me, it's mind-boggling. in those 23 cities, or mega cities, 10 million more, only 2 of them are in the United States, it's a good guess and a game to play with your seatmate, say, what are the other 21? How much water do we use? Well, New York City uses 2.8 billion gallons of water a day. Los Angeles, 2.43. Guess what? Shanghai only uses 7/10 of a billion gallons a day. Why? What happened if they use the same amount per capita as we do in the United States? If you have to carry water, 5-gallon plastic bucket, or these very neat barrels that they developed in Africa, where it's like a grass roller. It's filled full of water, so you go and take it to your spring and then haul it back to the village. How much would you use in a day? It's very different. In Phoenix, Arizona, the requirement to be enough is 250 gallons a day per person. So when we think about ecological design, are we going to have people in the United States use 5 gallons per day? There's no way that's going to happen, right? But how much do we need? Well, it turns out that the average residential user in the United States generates 40 to 60 gallons of wastewater a day. They basically take about 80 gallons into the house. That's a kind of average. In some places like Kentucky, they only need 50. Phoenix, as I mentioned, is 250. So there's a range here. And the difference is that, it rains in Kentucky and doesn't in Phoenix, but the people in Phoenix are on the lawn like you have in Kentucky. And that's one of the reasons why we tend to use a lot more water per person out west. One of the amazing things for me, and you're in a wonderful part of the United States, and you realize that you're in a very special community because it has paid attention to what's happening to the environment. But the amazing thing is, when you look at the rest of the world, you realize that 2/3 of the population of the world doesn't have any wastewater treatment. I work in some of those countries, Mexico primarily, and basically what we see is raw sewage going into the rivers and streams, which, by the way, goes to irrigate the crops that come back to the United States. Is it important for us to see that Mexico gets good wastewater treatment systems? Do we have any interest in helping our neighbor in this case? The population of Mexico, by the way, which is over 100 million people now, only 7% of the population has wastewater treatment. The reason, there are many of them, and they would like to have political and economic issues intervene, and it's a fascinating challenge. It's taken me 8 years to train people to be able to do stuff down there. And, it's slowly proceeding. And we'll talk more about what does it take to get changes to take place even in our own backyard. The Boston Municipal Wastewater Treatment Facility dumped 370 million gallons per day. I don't want to get the United States off and say, hey, we're not doing a good job. We dumped 370 million gallons per day of wastewater in the Boston Harbor, and only treatment was provided for about 30 to 40% of the total pollutants. To fix that problem cost the city of Boston $1 billion. So that's kind of the scale. Now, what if we had to do that in China with 1.3 billion people? Scale of the problem again. I just want to give a sense of how big this issue is. And this is just wastewater. Municipal treatment systems in the United States treat 36 billion gallons of water per day. To build those systems, which was funded in the Clean Water Act beginning in 1972, the U.S. spent $400 billion to do that. The bill is now coming due. All those wastewater treatment plants need to be replaced. They're running out. They've gone through their useful life cycle. They're only supposed to be good for 20 years. It's 28 years now. Okay, what are we going to do? Where's this money going to come from? Every day we spend $72 million on it. And the energy required, this is mind-boggling, 40 billion kilowatts an hour. We can't even conceive of how much electricity that is. One of the things that I've been working on is this carbon sequestration issue. So I looked at how much carbon we're putting into the atmosphere to generate that electricity to treat our wastewater. We put 15.8 million tons of carbon into the atmosphere to treat that wastewater. We put more carbon into the atmosphere than we take carbon out of the water with our treatment technologies. Why? Because in 1972 we weren't thinking about this issue. Nobody recognized the scale of the problem and the environmental impact it was going to have to run the electricity plants, coal-fired, to treat the wastewater. Nobody put this stuff together because nobody was thinking about it. Damn few people are still thinking about it. Okay? This is the challenge for you guys' generation. It's this holistic approach to what's happening to our systems. Just think about that, 15.8 million tons of carbon going up into the atmosphere. The sludge produced, briefly, that's 3,000 tons a day. Well, New York City, the way it deals with the sludge is it ships them on railroad cars all the way to West Texas from New York City. What's going on? And it's the way we think about things. It's this systems approach, a holistic approach, recognizing that interrelationship that I tried to show in that first slide about the four elements. Going to basic principles now, I'm going to suggest from my own experiences some very simplistic approaches to the way that we begin to deal with some of these problems. I mean, I want to give some encouragement in the sense, hey, there is some direction we can go. We can solve some of these problems. And it's more complicated than I'm going to lead you to believe after this 30 minutes, believe me. But let's just assume that some of these things, in fact, do work. The first thing is that if we have a water supply, the concept of limiting the sources of supply to the immediate watershed, okay? That statement, in a practical sense, say just avoid transporting water long distances. Now, that makes sense for a lot of reasons. One, the energy cost of transporting water, the infrastructure required, the fact that, if you're Los Angeles, you change the entire ecology of a region in Monroe Lake, for example. It used to be a great big green valley. It's no longer so. Los Angeles is the green valley. And we've changed stuff. Well, there's a real interesting question there. And that's why I said, asking this question, what are the implications for cities such as Los Angeles, New York, Chicago, or Muncie? If I said, hey, this is the rule, guys, you can't do this anymore, what happens to these kinds of cities? What happens to a city like Los Angeles where we're saying, hey, we can't take water from the state of Colorado to take care of their needs here? That's what these water fights are about, because I'm not the person saying it. In fact, the legal system is saying it, and we get into these big court fights that end up in an international courts of the U.S. Supreme Court over water. Or you go so far as the city of New York and says, anybody living around this reservoir has got to move. It's our city water supply. So they buy all the homes that used to be around this lake to protect the water supply. Okay? I mean, just think about the implications that it takes to deal with water. One of the ways you can help clearly is to minimize the use. And if you think about this would seem to be something that would have a major impact. And in fact, since 1980, when we began to be aware of water as a resource, well, we did encourage people to do this, and so the per capita use has actually declined about 5% in that 20 years. I'm going to suggest that we have a lot more to go. It should be mandatory that in every home you incorporate water saving and flow restriction devices. Now, in a place like Indiana, it's hard to believe that there's a thing as a water shortage. Well, what's the economic cost of unlimited supply of water, or being in the position of saying, look, we're going to make sure that as Muncie grows or Indianapolis grows, they get all the water that they need. We're not going to put any restrictions on what people can run into their homes. What's the implications of that? Okay. We certainly can do it. I mean, that's what we're doing for cities like Las Vegas, Nevada. We're diverting huge portions of the Colorado River to be able to make Las Vegas exist as if it was not in the desert. Why do we want to continue to do this? Can we continue to do this? Water efficient appliances. Boy, there's some really good stuff out there. And I know some of you, especially the younger students, I think, are looking at those kinds of things that recognize that they can have significant impact by using washing machines. 2 or 3 gallons is all they require. If the current use is 50 gallons per day, what if we were designing for 25? Could we do it? Do we need to? We're going to do ecological designs, yeah. The answer is yes to that question from my perspective. Wastewater is clearly the consequence of putting water into a home or in any business or energy. We use it for all kinds of purposes, and we put a pollutant load, which is really out of the home, is a nutrient load. But when we design these things, as you heard my comments about how much energy it takes to run our current systems, what I would suggest is that the ideal wastewater treatment system had no equipment and had no energy inputs. In fact, that's what the natural systems of the world did. That's one of the reasons the weapons are so important to us, is because that's what they do on a global scale. They're the kidneys of the planet, if you will, and their role was to remove the nutrients that washed off the upland areas. They washed into the wetlands, they were sequestered there or recycled from that point of view. So the natural world does not have the concept of waste, and these nutrients are continually recycled. And in fact, you can do this job, as I personally had the wonderful experience of being able to do in this country and in Mexico, of designing treatment facilities that don't have any moving parts whatsoever, and doing fabulous jobs. My recommendation, in my experience, is it's definitely possible to rely on passive treatment systems that incorporate the ecologies of the pond, marsh, meadow, and woodland. Let's put Mother Nature to work. I mean, that's what's been happening for the last quarter of a billion years. The same processes that we need for cleaning up our water are already in place. And if we make decisions about intelligent technology, the informational content in the ecology of the marsh far out scales anything that we have in any man-made system. We just can't compete with the kind of intelligence that's locked up in the multiple DNAs that are in those kinds of ecologies. And there's this other aspect of it too, which is, gee, they can look nice as well. Okay, this is really important for the concept of regeneration. I think we're seeing regenerative ecology as being more and more a role in development processes. It's definitely possible to do this. We can turn cornfields that are monocultures into prairies with many hundreds of different species of plants. We can do the same thing with woodlands, where we would have monocultures of pines. We can have multiple species of trees. We can get any kinds of different kinds of trees and shrubs in a woodland environment. I've got to stress the point, wastewater can be used to create significant habitat. In fact, out west, the only source of wastewater to create habitat is that wastewater. We don't have any natural sources of water left to divert to create habitat that's been destroyed or removed because we're developing. So what we have left is the wastewater coming from our municipal treatment facilities to create that habitat. And that's been a very significant effort in Western communities to do that. Changing from wastewater to a resource just requires us to recognize that there are significant quantities of nitrogen and the P and the C, the nitrogen, phosphorus, and carbon, which are essential for life. If we look at it, hey, here's water, which we need for life, and here's these essential elements that are in there as well, we can begin to see that we can use these things here to assist some kind of ecology, for example, a prairie, when you do it on the land application. So taking advantage of these resources rather than regarding them as something to be gotten rid of is really important. And right now, for example, the city of Indianapolis takes the phosphorus out of the water through chemical precipitation and then buries it in the landfill. And then the farmers here in Indiana buy rock phosphate from West Africa. Okay? So instead of figuring out how we can take advantage of all the phosphorus that goes through a big city like Indianapolis, what have we done? We're mining in West Africa and shipping it in ships all the way across the Atlantic Ocean to bring it back where it started from. Okay, how do you change that? Okay, all those people that are under 30 years old, they can deal with that problem. Land application of wastewater can be used to create prairies, woodlands, and marshes. I got to stress that again. You know, we know how to do this. We're getting good at it. Now, the prairie or marsh that I create isn't the same one that Mother Nature does. I don't want to give that impression. You know, we're starting to do this, but we know over time diversity increases in what we start with. We see diversity changes. We know that it's getting seeded by birds bringing in seeds, for example, or wind blows. So things are changing in that respect because of the interaction with the natural world. But the fact that we can do these things and they actually stay in place and do work is very, very encouraging to me. And we get wonderful clean water out of it too. Okay, the other concept is to keep treatment near producers. You know, one of the concepts we used to have, for example, it's still being applied in Ohio, you run a big sewer interceptor from the city of Columbus halfway to the city of Cincinnati, and Cincinnati runs another one toward Columbus. And you get everybody in between on a big sewer system with discharges on the Ohio River, or the Woollen. It's not the Ohio River in Columbus, I forgot what it is. But that's the way you would do it, okay? Well, it's crazy in a sense, because what we're doing is we're driving these great big 80-inch, sometimes 12-foot diameter concrete pipes, 2 of them, through the landscape to collect wastewater from the surrounding community. So if we keep it close to the producers, we can also put the water that we treat back into the same landscape. One of the things that we found over the past 28 years is that 3/4 of the cost of treatment is in the collection system. All right? So if we decentralize these systems, put them close to the community generating the source of wastewater, we can make them smaller, we can make them more efficient, and we can cut down on the cost of how far we have to run these major sewer plants. Okay? Reason is that looking at this picture here, the top picture shows a gravity sewer, and I've crossed a creek. Arroyo is the word we use out in New Mexico. Those of you Spanish may recognize it. But when we go under the creek with it, we've got to do this a lot in a place like Muncie. When we go underneath the creek or the stream, we got to make that sewer line, the conventional gravity sewer line, drop down, in this example, 13 feet. And this new sewer technology called small diameter systems, we can go under the creek and then back up again. And we don't have to dig that deep trench for the rest of the way to the sewer plant. So the new concept, it's a way to use fewer materials, which is a design concept. It's a way to keep the wastewater in inexpensive conveyances. And more importantly, we get away from this kind of machinery. This is, Muncie's got these, Indianapolis has got these. These are great pieces of machinery, by the way. They're very efficient. They were developed to solve the problem that conventional sewers have, because they clog up with all kinds of junk and trash that get into them. So, but engineers are good at this. We're great at solving problems. What do? We develop these wonderful vacuum trucks, which basically are big giant vacuum cleaners to clean out our sewer line. It takes 3 guys to run these machines. It costs $250,000 for that truck. And it's a marvelous piece of equipment, but it doesn't solve the basic problem. All right? We're still doing sewer systems and sewer technologies that are 2,500 years old. And rethinking the problem. How do we do this differently? How do we do this better? Do we need to get more and more sophisticated equipment that we use to clean out our sewer lines, or do we just change the way we do them? Keep it simple. Boy, that's a great design technique. You know, that really works. Turns out that what we implement if we use natural systems isn't simple in this sense, but it's simple in that we don't have to understand the kind of interrelationships between all the species that exist in a system like a wetlands. We don't have to worry about that. Because once you put it together, what we know about natural systems is they're self-maintaining, self-organizing, self-regulating systems. So Mother Nature can do it. We don't have to maintain that truck. Use environmentally benign materials. Okay, that makes sense. You know, an example for me is HDPE pipe, high-density polyethylene pipe, instead of PVC, polyvinyl chloride. Chloride PVC pipe, which is commonly used, everybody's got it everywhere. It's a ubiquitous material. That stuff is made with chlorine, which has very, very serious environmental consequences. Avoid machinery. That's why. Machinery, somebody's got to maintain it, and it uses electricity. It's a real hassle. You can get rid of it. Get rid of it. An interesting concept. Wastewater leaving your site, your community, or your city should be as clean as the supply that you got into it. God, what a concept. If your drinking water comes from the Ohio River, where would you rather live? Pittsburgh or Cincinnati? You want to be upstream, right, as close to the source of clean water as possible. By the time it gets to Cairo, Illinois, it's been through people's intestines 8 times by the time it gets down there, okay? Now, we'll clean it up on the way, but, gee, what do you think happens to the water by the time it gets down to a place like New Orleans, okay? Do we want to even think about it? An interesting case, this happened in New Mexico. the Isleta Indians downstream from the city of Albuquerque, this is a city of 360,000 people, successfully sued the city to say, hey, look, we're entitled to the same quality water you guys get. The intake for the city's water supplies is upstream on the Rio Grande, above the city of Albuquerque and also above the city of Isleta. Well, they treat the water, runs through all the city pipes, then it goes through the sewer system, and then downstream to the Isleta Pueblo. And the Indians said, hey, wait a second, we were here before you guys. We're entitled to clean water. Okay? They won the case. The city of Albuquerque has to make it as clean as what it comes in out of the river. What if everybody had to do it? What's that going to cost? Stormwater. Volume of water leaving the site should be the same post-development as prior to development. Okay? If you build buildings on the site, you increase the runoff coefficient. So when it rains, more water runs off. All right? So what's your responsibility to everybody downstream? Well, as we know, you create floods. That happens in every community. That's why there's regulations in place requiring detention ponds, etc. So how do we deal with this? This is a design issue. It's part of your training if you're a landscape architect, an architect and civil engineer. And we have all kinds of things that we're beginning to understand about how to do this better. And so there's all kinds of things that we can do. We can store it, put it in cisterns. Gibraltar runs totally on cisterns. That's how they get their water from rainfall, and they collect it and put it in cisterns. We can recharge the groundwater. It's a great place to put it. When it rains, instead of letting it run off, put it back into the groundwater. Change the permeability of the hard surfaces. What does that mean? Roads that are paved with asphalt have a different permeability than those paved with gravel, for example. Roofs, if they got a turf roof on it instead of a hard metal roof, it's a different runoff coefficient. It takes longer for the water to end up in your storm drains. So those kinds of concepts are really important, and it's things we have to do now. I mean, the regulations are coming in place, so they need to be implemented. There are lots of good materials out there that allow us to do that. Treat it. Boy, you got to treat it now. This is, in fact, we should have always been treating it, but we weren't. And the pollutants that come off a city like Indianapolis, for example, into the White River is a significant amount of all kinds of stuff. You know, copper from brake lines, for example. It's an amazing amount of copper that comes from brake lines. Well, we need to make our brakes with copper. No, we don't. We can make them differently. But who's paying attention? You know, I mean, how many brake manufacturers recognize the consequences of making brakes with copper end up in that river and kill all the fish? What about petroleum? All the products leaking gas lines, oil and grease that comes off of those cars that drive our streets. All of that ends up in the river. So now we finally recognize this is a serious problem in water quality. We're going to change it. So we've got to treat it. Right? So the water, the rule is basically, this is an ethical rule here. Water leaving the site post-development should be as clean as the water leaving the site prior to development. So if you had a nice green grassy field and you measure the water quality for that, and you come and build your subdivision or house, the stuff that leaves the site should be just as good as it was before. There's no reason for it not to be. And we can do it. We should do it. All right, the ways to do this basically is you make vegetated swales for drains. Don't use concrete curbs. Vegetated grassy swales provide treatment. They remove sediment. They trap things like copper. Wetlands are great for sequestering metals. We keep it in place. We don't let it go into our rivers. We can trap the sediments with basically specially designed manholes now that allow to remove both the hydrocarbons and the sediment. The other one is, this is another design concept, but if you think about it, if I'm asking everybody, hey, use natural non-degradable materials on all exterior surfaces. Okay? What happens to our buildings and the materials that we use in construction, eventually, if stuff wears off, paints, the vinyl siding, where does that stuff go? It doesn't disappear. It ends up in our water. It might be your drinking water, too. So you guys are designers now. Now's your opportunity to do something about it. You can change it, okay? Select the materials accordingly. Think about what you're using. Concrete channels, culverts, and pipes do not provide any treatment. And this concept of minimizing the time of concentration. What we were doing with Corps of Engineers' approaches to stormwater was putting everything into box culverts, concrete line channels, rushing the water as quickly as possible away from the site to generate. And what happened is that downstream, we were flooding people out. The other concept is that if you have a channel that's concrete, there's no treatment. If you cover that creek up and put it in a box culvert, put a road on top of it, and run it down Main Street, light, air, and the rest of it that is essential for treatment and keeping that water clean is no longer available. So there's a movement in the country to uncover our streams in our city. A good group of people that are regenerating those streams within the city. You know, grassy swales is a simple concept. Way it slows the velocity of water and keep it from concentrating at the same time providing its treatment. So curbs and gutters, I mean, you know, civil engineers love that stuff. We love to do that. That's a good way to get the water. What about grassy swales? How difficult is that for us to make that change? Wetlands also provide for storage. I mean, when you have a flood in the natural world, well, what happens is the water would rise in the wetlands because there would be a restricted outlet in effect along the water course. And we would have a rise in the water level. Sediments would drop out because the current slowed down. And then as the storm passed, the wetlands would drain. Wonderful way to treat water. Okay? Basic concepts using gravity. And then the surfaces of the plants provide substrate for the microbial populations that can break down the fluids that are in our runoff from our city. Okay, now you've heard the dreamer. Let's recognize really where we're at. And the question, I think, is a really good question. You know, I like to think of us, we're on the Titanic. And the question for all of us is, how do you perceive this ship that we're on? Is it before the iceberg or after the iceberg? Remember, the Titanic was unsinkable. It was state-of-the-art technology in 1912 and it was launched. And the engineers of the time, the people that designed it, thought this was absolutely the best of the world had to offer. It was clearly unsinkable. There was no question. It was never going to sink. Well, we can talk about the planet in the same way. Do we have an unsinkable planet? Or, gee, can it sink? And when I look at what we're doing, what I see the challenge for us is to recognize, yeah, there's the analogy of the Titanic is a great one, because if it says we're after the iceberg now conceptually, we know where we are in terms of the planetary ecosystem. We can begin to recognize that we shouldn't be trying to do an unsinkable ship. What we should be trying to do is be able to design something that can avoid the icebergs. And that does make provisions in the event that we do run into icebergs. If you have an ecological collapse of an ecosystem, what are we doing to be able to restore it? What are we being able to do to make it more robust, for example? What can we do for the watershed of the White River in Indiana to make it more robust and less likely to succumb to an environmental event like an ice freeze for extended periods of time, or a warming period that caused many of the trees, for example, to die out of some diseases. What are we doing in anticipating these kinds of changes? What are we doing to anticipate the iceberg? We're dealing with people who, in many ways, when we're trying to make these changes, are in that state prior to the iceberg. They're on the Titanic. Everything is fine. Our regulatory framework, Uniform Plumbing Code, Uniform Building Code, National Electric Code, all of the things that are the basis for regulating the way we do things now are based upon the idea that everything is fine. Okay, so when you go and suggest new ideas like, hey, I want to use a vegetated swale, try to do that in any community today and see how receptive you're going to get. I'm working in New Jersey on a project now, for example, and on stormwater wetlands. They've never done it, they've never seen it, they have no way to regulate it. They like the idea. So at least I have a positive approach. Unfortunately, it's not the first time it's been done. All the surrounding states already have regulation. So these guys are going to come along just by sheer force of their peers. But this is a reality for change. How does it take place? How do we work with the people who are going to say, hey, things are fine. We don't need to do things differently. And well, I got to tell you this is personal experience. Change is difficult. It's difficult for all of us. Look at your own personal life and see how difficult it is to change the way you do things. And, you know, here's a picture of state-of-the-art technology wastewater treatment system. You know, wonderfully highly organized. Here's another picture of another wastewater treatment system. Thank you very much. Come on, anybody can take this on. Yeah. Question was, have I done any work with regulatory agencies? Yes. And actually, one of the states is Indiana. I worked with IAM on regulations for implementing constructive levels in the state. There was a group of people there, not the whole department, but there are people there that are receptive to the ideas. So change is possible.
What is the difference in the volume of land use you need for existing technology versus what is?
That's a great question. I mean, I love that issue. The question is, what is the difference in land requirements between conventional current use technologies and the kind of technologies that I propose, natural systems? It's a significant difference. Basically, the story is we're changing land for energy. The city of New York treats 1.3 billion gallons of wastewater a day, and we'd have to have 4,000 acres of land to do that one, for example. But where's 4,000 acres of land going to come from the city of New York? So part of the problem is the way the cities have grown up and the way we've dealt with wastewater is that we need these high-rate, high-energy technologies to provide treatment. Unless you took over the North Shore of New Jersey, which happens to be totally trashed and used to be wetlands, and restored it, the 4,000 acres is easy to find. So the issue is, yeah, it does take land, but once you go to a natural system, the energy bill goes way down. And when you're committing yourself to high-rate, high-energy technologies, you're committing yourself to that indefinitely. It's a forever price tag. Once you acquire the land for a natural system, it's a one-time cost. And it is clearly has this environmental benefit that I've mentioned here with carbon, atmospheric carbons, and habitat issues as well. Now, you're taking land in exchange for energy. And there's actually formulas to do that. I may talk about that tomorrow. Any more?
The Chinese response to your presentation,
Yeah, it was very interesting. I think it was the same one that, in the essence of the question, you know, the solutions that come out of the grant program in 1972 Clean Water Act, when we weren't thinking about it, they're adapting or probably going to be considering primarily the conventional technologies that are in place now. Australians have had an impact on them. And basically, my sense is that the way they're currently thinking is, yeah, they're going to go, the problem is just too big. I did a calculation about how many, something like 24 hectares of land that would take. It's not impossible to do it at all, but you know, if you have 17 million people in the city and 1.3 billion in the country, you have a different view of land than we might hear. I don't know where it's going to go. We think we're going to be able to do a green demonstration, but whether it was adopted citywide, it's a hard switch, very difficult.
What are the best models you can think of this practice?
Best models for practice?
I mean, like in a certain city or town, this is
Oh, working examples. Well, turns out there's one, a small scale one. This is one of the ways we can save land. It does have an energy cost because it's the greenhouse. It's the PAWS project right here in Albany. That's been here since 1989, I think. Fish Royal Lakes up in LaGrange County. There's a couple projects around Howe. There's one over by Valpo. Big scale projects, City of Orlando, 20 million gallon per day facility. That's their wildlife park. City of Arcata, California has been very instrumental in this kind of technology. They've done a system where it's now part of the public parks. It's a salmon raising and oyster farm. So they totally integrated it. It's developed by biologists, not engineers. And their thinking is based upon these biological principles. There's a bunch more in the surrounding areas. I can get you a website. DPA is a great website. Yeah.
You've got existing seeds, you've got infrastructure. How do you see the transition to natural systems?
Oh boy. You know, that's the real challenge, isn't it? Yeah, I'm sorry. Good question. If we have an existing city, let's take Indianapolis. How would you convert an existing city like Indianapolis from conventional technologies, conventional conveyance, ways of transportation, et cetera, et cetera, et cetera, to natural systems? How do you go about greening up a city? You know, I don't know the answer to that. I mean, it's truly, well, I think we're beginning the process to understand what the technologies are right now. I think it's your generation that's going to have to come up with the answers. Yes.
In an arid environment, do you see, how do you be sensitive with this wetland solution? I mean, do you totally go into recharging the aquifer and keeping it something internal underneath? Because you would change the habitat if you tried to address an environment using that scenario.
Yeah, the question is, I think I'll generalize it. How do you make natural systems specific to the region in which you're applying? Wetlands, for example, in southern New Mexico or Arizona, where we're in a totally arid environment, wetlands are not common phenomenon. They're much more common in a place like Indiana. So what do? Well, clearly we're not going to use a land apply to water in Indiana and grow alkali saccatone, which is a grass, clump grass that grows out west. Or we're not going to do the short grass prairie with buffalo grass. We're going to do something different. You do something, when you apply these technologies, the ideal solution is to look to see what Mother Nature has done. If there's any good examples around, you look for those. And they become your basis for the scale or the level of perfection you would like to reach. In New Mexico, we actually have wetlands. They're very small, they're not very large, and what we rely on then is the local plant community from those wetlands in that part of the state. What we try to do with the water there is reuse it for irrigation for native species. Okay, it's a great thing for us to do there. Just a little bit of water makes a big difference. So instead of growing a Kentucky bluegrass lawn, you can grow a buffalo grass, for example, which is a native shortgrass prairie.
But the evapotranspiration, are you thinking that because of the scale, some of them have to be subterranean?
No, it's quite small, actually. The size of the wetlands, in an arid climate like New Mexico, where I live, in the northern part of the state, it's only about 7% of the total amount of water. In the southern parts, where high-rate places like, let's say Las Vegas, 4 inches of rain a year, 108 inches of evaporation, it's only about 15%. So anyway, the design is follow Mother Nature. And by the way, there's lots of wetlands plants in southern Nevada, and we are in fact doing a big restoration project there. 21 acres of wetlands. Used to be a lot in Las Vegas, surprisingly. And we are doing some restoration based upon the local ecology, using nuisance water runoff from the streets because people are overly irrigated. Any more questions? Oh, good stuff. Yeah, one.
Kind of on that same line, and on that issue, like say you work with harsh players and what would go a little bit more warmer, so we'll have effluents going at us.
What happens in the wintertime for these systems, yeah. Most of the work's done by the microbial community and not the plants. I think that's a really important concept. People have
had mentioned the number 90%. I don't think anybody actually knows what the contribution is. But the plants provide substrate primarily. They have a lot of other very important functions, but that substrate, the root mass, or the stems and the standing water, wonderful place for the non-motile species of bacteria to attach themselves to. And they are responsible for removing and recycling the nutrients that come through that stream. So when you do the design, you design for the environmentally worst conditions. January in New York. January in Clinton. And that's what you look at for the sizing. Okay. So 4,000 acres turns out to be enough for the entire city of New York. Yes.
Are some of these wetlands going to get being harvested for some of the biomass? Is it an added benefit?
Yeah. Yeah. There's all kinds of possibilities there. Some of them were something like one, but it's that kind of thinking. Yeah, what value can we get out? That was an industrial ecology example. The one I was specifically talking about becomes substrate for mushroom production. Okay. Yes.
Do you see any occurrence of the accumulation of pollution in the wildlife and plant life?
Yeah, those are really important design questions. The classic example that we all learned from was Kesterson Marsh in California. Kesterson Marsh ended up sequestering selenium, and it was a free water marsh, not a subsurface marsh. The birds ate the plants that were contaminated with the selenium. Now we know, gee, if you got birds and you got selenium, we got to keep that from getting into the birds. So those interactions are really important. When you design natural systems, there's an impact that isn't just clean water. Habitat's very significant, and you want to pay attention to that, what's in the water. I'm done.